last class, we saw that the for the plane stress case, we saw that del square of tau xx plus tau yy is equal to minus of 1 plus mu times del dot rho times d. Okay, so this was the equation that we derived. So if you recall, this derivation of this particular equation involved both the equilibrium equations and the compatibility relations here. Fine. So now let us look at the plane strain case. So now if I look at the plane strain case, then so plane strain. So as we said that we just replace mu by 1 minus mu, right? Last time I indicated that E should be replaced by E by 1 minus mu square and mu should be replaced by mu by 1 minus mu. So then this particular equation now will become del square of tau xx plus tau yy is equal to minus 1 by 1 minus mu del dot rho b. So that is the modification that we get in this particular case here. Yes, and now so for the plane strain case, now your epsilon xx, epsilon yy, gamma xy are functions of xy. Functions of x and y, and our epsilon zz is equal to gamma xz is equal to gamma yz is equal to 0 in this particular case. And so the remaining 5 equations are compatibility relations are satisfied. So remaining 5 compatibility relations are satisfied. So if you recall, in the last class I mentioned that the compatibility relations are violated. Out of the remaining 5, 3 equations were violated, if you recall, from in the plane stress case. But in the plane strain case, that problem does not occur. So here basically, if you make these assumptions, then the remaining 5 are satisfied and only the in-plane compatibility relation is used in order to derive this particular governing equation here. Fine. So, okay, so now we will introduce what is known as the Airy stress function. Okay, so this is very important topic now. So that actually helps us to solve these planar problems in a very convenient way. Okay, so that is what we will look at now. So Airy stress function. Yes, so let us look at this. So, so we'll assume that the body forces are conservative. Assume that body so what we mean by this body forces are conservative means that there exists a potential from which we can derive the body forces. So that means the rho bx can be written as del v by del x, and rho times dy can be written as del v by del y. And so this v is like a potential function, function. So from which you can derive these body forces here. So now if I write the equilibrium equations, then I will get, so let's write it here. So del tau xx by del x plus del tau xy by del y plus, so now this rho bx can be written as del v by del x equal to 0. Right? So then these two can be combined together, and I can write del by del x of tau xx plus v plus del tau xy by del y is equal to 0. Okay. And then similarly, the second equation can be written as del by del y of tau yy plus v plus del tau xy by del x is equal to 0. Right, and so now what we will do is that we will now write the stress components in terms of the Airy stress function, which we will introduce now. And then once we introduce this Airy stress function, then you will see that these equilibrium equations are automatically satisfied. Okay, so we will choose now, we will write there tau xx plus v as equal to del square v by del y square, then tau yy plus v as equal to del square v by del x square, and tau xy as equal to minus del square v by del x del y. Okay, so we will choose the or we will write the stress components in terms of this function phi, which is the Airy stress function. So here in this particular case, your phi is the Airy stress function. Okay. So if you write these stress components in terms of this Airy stress function in this particular way, then you will see that these equilibrium equations are automatically satisfied. Correct? So you can just substitute it here and you can easily verify that these equations are satisfied. Okay, so so what we do now is that we will now substitute these components of the stress into the governing equation for the plane stress and plane strain that I wrote at the beginning of this class here. Okay. So what you will get, let us just rewrite that here. Yes, so substitute, so this corresponds as 2. So substitute these 2 into the governing equation, so that is del square of tau x plus tau yy is equal to minus 1 plus nu del dot rho. So that is dot rho d. Okay, so what you will get is that and then we have said that rho b is equal to del of v. Correct? So if you now substitute it into this, then what you will get is the following. You will get that del raised to 4 phi, which is del raised to 4 phi by del x raised to 4 plus 2 del raised to 4 phi del x square del y square plus del raised to 4 phi by del y raised to 4 is equal to 1 minus nu times del square. So this is what you will get. And now for plane strain, you can replace it by so for plane strain, for strain, replace nu by 1. So this is for plane stress. And then similarly you can do this for this one also. So if the body forces are 0, if body forces are 0, then we'll get that they'll get del raised to 4 phi is equal to 0. So this is known as the biharmonic. So if del square phi is equal to 0, then that is called as harmonic, right? Because then phi is said to be a harmonic function if del square phi is 0. So here, since del raised to 4 phi is 0, so this del raised to 4 phi you can also write as del square of del square phi is equal to 0. So that is first you operate on phi with the del square operator, and then whatever you get, you operate once more with the del square operator, and then you will get this del raised to 4 phi equal to 0. If body forces are the weight, for example like gravity, then also you will get the same thing. So suppose if body force is simply gravity, then you will get that V is equal to minus rho g y. So suppose if this is x and this is y, and g is pointing in this particular direction, then you will get that V is equal to minus rho g y. And then so in this particular case also, del square V will be just 0. Okay, so this implies that del square V is equal to 0. So in this case also, you will get that del raised to 4 phi is equal to 0. So the governing equation remains the same, but here you will see that there is a plus V. So this is not the same as having a 0 body force, because in the expression for the stress it will change. All I am saying is that the governing equation remains the same. If there is gravity is the body force, so the V will still have to be substituted here, and then this expression will change. So it is not the same as 0 body force. Only this governing equation remains the same in that particular case. So let us just write that here. So you will get here in this particular case, you will get tau xx is equal to del square phi by del y square plus rho gy, and then tau yy will be equal to del square phi by del x square plus rho gy, and tau xy will be equal to minus del square phi by del x del y. So this is the shear stress component doesn't get affected by the body force, because that V is entering only into the expressions for the normal stresses. The other stress, shear stress, does not get affected by that. Okay, so let us now move on to the next thing here. So let's see. Yes, so let us look at now how to solve certain problems using this airy stress function approach. Okay, so let me just summarize this. So basically, what we have done is that using a combination of equilibrium and compatibility relations, we have come up with a stress function phi, which automatically, so if which has this governing equation del raised to 4 phi equal to 0, and if this equation is satisfied, then automatically your equations of equilibrium and compatibility are satisfied. Okay, and then so what you have to do is that you have to solve this particular equation, correct, del raised to 4 phi equal to 0, and find the constants in the solution such that the boundary conditions are satisfied. correct? And then once the complete solution is found, then you can recover what the stress components are by simply plugging it into this formula that I have written here. So let us take a look at some examples. Maybe then the situation will become clear. One. So imagine that there is this bar now, which is loaded by shear tractions on the bottom edge here, and then the top edge is traction free, and even the side edges are also traction free. And now we want to find out what is the solution corresponding to this. So So this problem is actually taken from Timoshenko and Goodyear. Page 63, problem 4. So this is what I have done. So in this case, we will write phi as equal to S times 1 by 4 times xy minus xy square divided by 4c minus xy cube divided by 4c square plus ly square by 4c plus ly cube divided by 4c square. So this is the force. So this is the Airy stress function that is given to us. Okay, and then now we have to figure out whether this solution satisfies all the boundary conditions. Okay, so now you may wonder that how did we get this? Okay, so you will see that first of all it satisfies the biharmonic equation. So if you actually compute del raised to 4 phi, you will find that it is equal to 0. So basically the way Timoshenko and Goodyear found this particular function is that they just tried out a polynomial, correct? So this is like a polynomial in x and y. So they just tried out various terms in the polynomial expression, and then they adjusted these constants so as to satisfy the boundary conditions. Okay, but now you will see that actually it satisfies most of the boundary conditions, but not all of them. Okay, so in that sense, actually we will see that this is not the perfect solution for this particular problem. Okay, so as I said that you may wonder that do we have to keep doing this kind of a guesswork? Okay, so the answer is that you don't have to do this kind of a guesswork. There is a systematic way of deriving the Airy stress function approach, but that is a little bit too complicated. So in the beginning, right now, because this is a first level course, we will not get into the more systematic method, which is more complicated. We will simply look at some Airy stress function which is given, and then we will try to see if that is satisfying certain boundary conditions or not. Okay, so that is the way, that is the approach that we will take here for the moment, as I said. But because if you go by the very systematic approach, then that is like a Fourier series. So there are an infinite number of terms in that, and then sometimes it can be like a complex valued function. So complex valued in the sense that so it will have both like some complex term and its conjugate, so that finally the result is real because all the variables are finally real. But So you can get the idea that it gets very complicated there. So we will not get into that systematic method, but if you want to know more about that systematic method, then the chapter 6 in my book will give that systematic method. So right now let us just try whether this proposed solution satisfies all the boundary conditions or not. Fine. So now first is your tau xx is equal to del square phi by del y square. So that is equal to s times minus x divided by 2c minus 3xy divided by 2c square plus L by 2c plus 3Ly divided by 2c square. Then tau yy is equal to 0. That's just del square phi by del x square, so that is equal to 0. And then tau xy is equal to minus del square phi by del x del y, so that is equal to minus s times 1 by 4 minus y divided by 2c minus 3y square divided by 4c square. So now let us verify whether the boundary conditions are satisfied or not. So first one, at y equal to plus minus c, okay, you will get that, or first let me just do plus c, we will get that tau xy is equal to s. So if you substitute y equal to plus c, then into this particular expression, then you will get tau xy equal to plus c. And then at y equal to minus c, you will get that tau xy is equal to 0. Okay. So first of all, how do we even figure out what the boundary conditions are, right? So here you will see that, so let us take this particular phase here, right? So on this particular phase, the normal is 0, 1. Right? So this, the unit normal n is equal to 0, 1. On this particular phase, the unit normal n is equal to 1, 0. On this particular phase, your unit normal is 0, minus 1. And on this particular phase, again, your unit normal is n is equal to minus 1, 0. Correct? So now, what are the appropriate boundary conditions to be imposed on this particular surface here? So if you take now your tau xx, tau xy, tau xy times tau yy times this normal, right? That is times 0, 1, right? Then you will get that this is equal to tau xy and tau yy, correct? So the boundary conditions are to be imposed on the tractions, correct? So because this is a surface on which the tractions are applied, and so these are the appropriate traction components on this bottom surface here. And then here you can see that your tau xy is prescribed to be s, correct? So that is whatever here. So this and so this is prescribed to be equal to s and 0, correct? Because there is no normal component of traction that is applied on this particular phase. So suppose you imagine that there was some normal traction P, then your tau yy would be equal to P in that case. But here, since there is only a shear traction that is being applied, this is the boundary condition. This is the appropriate boundary condition on this particular edge. Then let us take this particular edge here. So for the right edge, so let us write. So for this particular edge here, let me just draw this like this. So here you will have tau xx, tau xy, tau xy, tau yy times 1, 0, correct? So and then that is equal to tau xx and tau xy. So these are the two traction components, right, on that particular edge here. And so in this particular case, if there had been some normal traction that had been applied, then that tau xx would have been that value. and if there had been a shear traction on this particular edge, then the tau xy would have been that particular value. But now, in this case, nothing is applied, right? There is no traction that is applied. So basically, your boundary condition is that tau xy is 0, tau xx is 0 and tau xy is 0 on this particular edge here. So this is tau xx, sorry. So let me just try that. Yeah. So tau xx is 0 and tau xy is also 0 on this particular edge. Similarly, so on this particular edge, you will get that tau xy is 0 and tau yy is 0. On this particular edge, you will get that same thing. Tau xx is 0 and tau xy is 0 because there is no traction that is applied. So that is what basically we are verifying. So now here you can see that tau xy is s and tau at y equal to plus c, you get tau xy equal to 0 and you get tau yy also is equal to 0. Right? And here also you get tau yy equal to 0. So you can see that the boundary condition on the top and the bottom surfaces are perfectly satisfied actually, right? Okay, then let us see. So, but now, as I said, that there was one shortcoming. So let us try to see what that shortcoming is. Right? Okay. So the tau xx at x equal to L. So second thing. Now let us write that. So tau xx at x equal to L is equal to 0. Okay. So that part is also correct, and the only problem is now the tau xy should also be 0 on this particular edge, right? Because there is no traction that is acting there, and so let us write that. So third part is that tau xy at x equal to L is equal to s times 3y square divided by 4c square plus y divided by 2c minus 1 by 4, and that is not equal to 0. Correct? So this is the shortcoming in this particular solution. So basically this Airy stress function which is proposed satisfies most of the boundary conditions, but not all of them, right? So we can see that it actually violates this particular. So essentially what it means is that this proposed Airy stress function is not an exact solution for this particular problem here, right? So basically on this particular edge, you have a distribution of a shear stress which is of this particular kind here, right? So this is like this. So you can see, so there is a negative shear component along this particular this one, and then there is a positive. So I'm just drawing the magnitude of that shear here. So one part is negative and the other part is this one. So this is the imperfection in the solution, in the sense that it doesn't really satisfy. So actually that was the problem, that you basically determine whether the Airy stress function that is given is correct or not, right? And so we have determined that it is by and large correct, but not fully correct, right? So that's why, so it's not actually a solution to this particular problem here. Let me just indicate how you can compute the resultants of forces also. So you don't need to do that, but in some cases you may need to do that. So suppose sometimes somebody may say that the resultant force is V or something like that, or the resultant moment is M. So you need to know how to find the resultant forces and the resultant moments from the traction distributions, right? So let us look at that now. So we have seen that basically the resultant force, so the resultant force, right, resultant force is equal to integral of t times ds, right? So on a given surface, the way you find out the resultant force is this one, right? This is what appeared in the balance of linear momentum, and the resultant moment would be equal to integral of x cross t times ds, right, over s. So this is what appears in the balance of angular momentum, right? right? So these are so this is how you should compute the resultant forces and moments. So for example, suppose if I wanted to compute the resultant shear across this cross section here. So suppose if I wanted to compute the resultant shear along this edge here. So then in that particular case, I will write it as minus C to C of tau xy times dy. Okay, and so this let me just see this. So this is equal to minus C to C of minus S times 1 by 4 minus y divided by 2c minus 3y square divided by 4c square. So this is at any x, okay, at any x. See, because this tau xy, it doesn't depend on x. So typically we would have to calculate it at some given x when it is a function of x, but in this particular special case, it doesn't depend on which x you are computing it, because this is independent of x. So it's the same at all sections. And so if I integrate this, so this is over dy, then if you carry out this integration, this is equal to 0, and that is expected, right? Because see, if you draw a free body diagram of this particular body, you will see that there is no resultant shear force along this particular direction here. Right? Okay, so fine. Then xy, yeah, dy, and what about the axial force? Okay, so so this is the shearing force. This is a shear force at a section, and let us calculate the axial force at that section also. So axial force would be integral of tau xx times dy. So this one is also coming from this, right? So this is the ty component. So that is ty is nothing but tau xy, right? So that we had shown it there. And then similarly on this, so on this phase, right? For example, we have seen that Tx is tau xx and Ty is tau xy. So whatever we have computed is actually the Ty component or times ds, and now we are computing Tx component, which is tau xx times dy. And so if you carry out this particular integration, you will get that is S times L minus x. So this is at a given x. So if you draw this free body diagram of this, right? So it is like this now. So the moment, so there is this one, right? This one. So the moment due to the axial stress is balancing the moment due to this shear. And so finally the any particular subpart of this particular body is in equilibrium. So that is what we require. So here maybe I'll just write that here. So this is a so this here the axial force, S into L minus x balances the axial force due to the shear interaction. So here basically this force. So maybe I think I may have drawn it in a maybe just draw it this way here, so that now I'm considering this particular part, I suppose, right? This particular part. So there is a shearing traction on the bottom here, and then there is some axial force here, right? So and there is nothing on this particular part. So this axial force balances this force due to the shear. Okay, and so finally you will get that it is equal to 0, right? Finally, because see, finally integral of TdS should be equal to 0 because it is a static problem, correct? And there is no body force in this case. And similarly, the integral of x cross t over the entire surface will be equal to 0 because again it's a static problem. But here what we are doing is that we are computing it on one surface, okay? And then as I said that the integral of this and the integral of this will balance, and then finally you will see that integral of TdS is equal to 0. So these are some of the things that how to compute the resultant forces, resultant moments at a given section. So that is something big. Then let us compute the resultant moment also now due to the shear stress here. So as I said, that is your x cross t. Correct. So let us do that. So the moment m that is due to the axial force here. So this is your tau xx. Okay. So now let us see. So this is your y, right? And then direction, and then this is your x direction. So this is starting from here. So this is your y, and this is your x. So let me remove this arrow here. So this is your axis. Now we want to find out what is the moment due to this traction here. So as I said, that is integral of x cross t times dx. Correct. So if you write x as xy, correct? You write this as xy, and then that cross tx ty, correct? And then now you compute the resultant moment. So right now I am computing the resultant moment only due to this particular component, y times this tx. Okay, so this will be equal to tau xx times y times dy. So let us assume that the thickness into the board is unity. Okay, so actually here you should have an area element, but because I am assuming that the thickness into the board is unity, so that is actually multiplied just by 1. So this 1, that is the thickness, that represents the thickness into the board. Fine. So if I now compute, if I carry out this particular integration, then I will get that is SC times L minus MC. Okay, and so this is exactly the moment that is exerted due to the shear traction also. Okay, and so the moment due to this axial force is balanced by the moment due to this shear traction. And so finally your x cross t will be equal to 0 on that particular this one here. So this is how we compute the resultant moments also in this particular case here. Fine. Okay, so to summarize this, so what you have to do is that basically if you are given an Airy stress function, then you should compute the coefficients, right? So let us say that you have found out by guesswork some of the polynomial terms, and then there are coefficients associated with that. So the way you find the coefficients is that they should satisfy certain boundary conditions, right? And so here we saw that they have to satisfy the traction boundary condition. So here in this particular problem we considered it was a pure traction boundary value problem. But suppose if there are, a part of it was displacement, right? Then we would have to verify those displacement boundary conditions also. So you basically find the constants in the Airy stress function such that they meet the boundary conditions. Okay, so that is the idea in how we do this. And then after all the constants are determined, you can find out what is the resultant force or the resultant moment at a given section by using these x cross t or integral of t times ds. As I said, that the systematic approach. So here in this particular case, we saw that this Airy stress function did not meet certain boundary condition. So if you use the systematic approach where it's an infinite series, we would be able to satisfy all the boundary conditions, but that approach is very complicated. So right now we will just look at approximation.